attend this session. Today, I'm gonna present my thesis project. The name of the project is Low Fatigue Designs and Deep Learning based classification for motion visual with potentials. First of all, we'll provide an introduction to BCIs, and then we'll describe different sorts of visual with potentials. Then we'll see three main contributions of this work, and we'll introduce some future works that are applicable in the field. First of all, there's a question that whether interaction between our brain and the outer world can be established without intervention of human's voluntary nervous system. And attempts toward this has resulted to emergence of brain-computer interface system. As you can see in the right figure, we have a brain-computer interface system within an AR augmented reality platform. And the EEG signals collected from the brain are translated into the commands, and these commands are used to control the outer system. And these BCI systems have a lot of applications in ranging from neuroprosthesis, which is a device to overcome neurodisabilities, to the P300 speller, which is a system developed so that the user can input text to a computer through brain signals and without using their limbs. And one of the non-invasive BCI is visual with potential based systems. As you can see in the right the right bottom. And as you can see, displaying visual stimulus to the subject lead to provocation of signals within the brain. Once we collect these signals, we can extract the pattern change after watching the stimulus. And these features in the EEG signals are called event-related potentials, or ERPs. We have different components of ERPs, and these are the most important components, like P1 or P100, N1 or N100, and P300. So visual MRI activity and dipole modeling supports the interpretation that the visual cortex is the source of these early components of VP. And they usually comes from the occipital or the parietal lobe of the brain. Another crucial VP component is P300, and which is a positive going deflection in the EEG signal that occurs about between 250 and 500 milliseconds after a stimulus onset. And it usually occurs in the parietal lobe. This feature is more related to the perception mechanism of a visual object. And here in the right figure, we see the mean topographic map at the individual peak of P300. So now we have the concept of steady state visual with potentials. SSVP is a response to the steady state visual stimulus modulated at usually frequency higher than 4 Hz. And different frequencies of flickering are assigned to different target or commands in this system. And targets are onset of the patterns appearing with constant frequency, like the black and white flickering. So SSVPs has become popular because of their fast and easy system configuration and strong provocation of visual brain signals. But despite their popularity, their utilization for practical applications, especially for assistive technology, is challenging because of eye fatigue, mental load, and the risk of epileptic seizures. And in this regard, this issue is addressed by development of flicker-free steady-state motion visual with potential, or SSMVPs. So the paradigms, for example, in the contraction expansion of checkerboard, like what we have shown in this figure, each ring switches the colors of its black and white board, and other rings do this action respectively in such a way that the subject imagines that the image is contracting or expanding, which means the movement starts from center of images and goes to the borders, and again, it comes back to the center. And this reciprocal movement, it works with ease on the brain. So frequency of motion direction change, as we mentioned, is equal to the frequency of SSMVP. Swinging, rotation, contraction, expansion, all of them can be considered as SSMVP simulations. So these SSMVPs have one major problem, and the problem is they have less accuracy compared to the typical SSVPs. In this research, we come up with three main contributions helping us to address this deficit of SSMVP. So before stepping into the contributions, let's take a look at this experimental protocol that we have used in our data collection. And when we design a new paradigm, it raises the question how to evaluate SSMVP paradigm in terms of the performance, accuracy, or visual fatigue level. And in this figure, we show the pipeline we use in our data collection to compare different SSMVP paradigms. So a stimulus displayed on the screen and evokes the EEG signal. We collect the signal as well as the fatigue score given by the participants. Then we pass the collected signal to the EEG signal processing module with 3 blocks. And then we'll describe this module later on. And then the amplitude of the power of the signal at the target frequency are computed as another reward for visual fatigue level. Then we use a classifier to identify the target where the subject has stared at. And finally, based on the accuracy of frequency or target detection, we come up with the accuracy score, which is used as another reward value assigned to the paradigm. Using these variables, these 3 variables, it can be considered as a feedback from each signal. The designer tried to update the videos, and we took the colors, contrast ratio, and the brightness of these videos to reduce the fatigue, as well as increasing the power of the signal at target frequencies. So to remove the unwanted component in our EEG signals, we have 3 main components. And the first one is the time domain filtering. We use the first 0 phase Chebyshev type 1, which is a bandpass filter between 2 to 40 hertz. We applied it to the raw EEG signals. We do it to smooth the data and also remove the high frequency artifacts. And we derive these frequency intervals from using the visual frequency band of the human. And this is why we assign this range. And another thing, apart from the time filtering, we provide a spatial filtering, which is a common approach in brain-computer interface to use topological distribution of signals to remove the components within EEG that are unnecessary for main goal, which is extracting the VPs in our case. And we use maximum contrast fusion for our most of our experiments. And this algorithm aims to obtain special filter coefficients in such a way that SSMVP energy is maximized and the power of the noise is minimized at the same time. Next, we have the frequency recognition block, which is chemical correlation analysis in our case. So the chemical correlation analysis, or the CCA, the question is how to detect the label of unknown signals. And we want to label these unknown EEG signals after these preprocessing steps. So we have 2 data sets called observation and reference signal. And the reference signals are sines and cosines derived from SSVP stimulation frequencies. And for each stimulation, we aim to find projection vectors like WX and WY applied to the observation and reference signals. And we want to find these 2 vectors in such a way that the correlation of the projected data sets are maximum. And finally, for each stimulation frequency, the correlation coefficient is calculated. And the final label of the unknown EEG signal is the stimulation frequency for which the correlation coefficient is maximum. So to address the main limitation of SSMVP, in the first chapter of our work, we designed 2 novel paradigms with collaboration of our department at Concordia, and we used the experimental pipeline described in previous slides to select and update high volume of design paradigms. Finally, 2 best designs are selected for comprehensive comparison with SSVPs. And in our novel paradigms, we used colors with low contrast ratio. So it will be easier for the subject to track the target and also focus on the movement for a long time. And this way, the contrast ratio is, oh, sorry, I don't know how to, okay. If you look at these videos, we make paradigms more complex to make sure that the half and the second harmonics are evoked properly as well. Because we use two types of motion, like contraction, expansion, and also radial zoom, which is the resizing of the red circles inside the paradigm. And according to the literature, these resizing evokes the half harmonics. So if we combine them, we can make sure that all the harmonies are evoked properly, and this enhances the performance. So in our experiment, subjects participated in tests for 2 rounds, and with 10 minutes break between the rounds. And each round, all targets are displayed one by one, and subjects are asked to look at the target where the cursor is pointing at. And experiment is repeated 4 times for each target, and we have 4 trials for each one. There's also 3 seconds break between the 2 consecutive trials. Next, we sketch the power spectral density of the Aegis signals. And as you can see, these the half harmonics of these Aegis signals are evoked, and the amplitude of the half harmonics is higher than the main one. And this is because the resizing is located at the center of the images, and it draws more attention. And for comparison of our results, we also compare our 3 paradigms in terms of the accuracy, information transfer rate, which is defined here. And also, we divide each trial length with different time window and plot accuracy and ITR across all of time windows. And a square-based contraction expansion paradigm outperform both SSVP as well as circle-based contraction expansion paradigm when the time window length is 4 seconds. And we will usually see a drop in accuracy between the first and last rounds of the experiment. And this is because distraction of the subject. Therefore, it will be a reliable criteria to assess the visual fatigue level of the paradigms. And again, a score-based has the lowest accuracy drop, which means it causes the least mental load among all the paradigms. So in the next chapter, we propose a coding algorithm and novel idea to integrate 2 frequencies within each target. And here we have shown the way to assign frequencies to targets, and 2 frequencies are assigned to each target and 1 single target in such a way that every pair of targets have at most 1 adjacent frequency. And 2 frequencies are called adjacents if when we are sorting these frequencies, the indices of these frequencies are adjacent. And in figure at the left bottom, we can observe the frames of these videos. And first, we have 2 main motions, the rotation and radial zoom. And after integrating these 2 motions, we get both motions without increasing the number of frames at 1 single paradigm. And if you look at the right corner, we compare the mechanism of our coding to FS, the phase shift keying modulation applied to SSVPs. And in this modulation of SSVPs, 2 frequencies within 1 target are displayed independently and in 2 different time intervals, like here and here. So, however, we can display both targets in our DFSS MVPs at the same time. And that way we can save the resource of time. So we also designed a new way of spatial filtering and frequency identification modules, which is compatible to our new paradigm design and coding algorithm. In this regard, we have 3 main reference signals and derived from 2 targeted frequencies or the SSMV frequencies. And based on these 3 reference signals, we can compute 3 correlation coefficients. And once we come across these 3 correlation coefficients, we can average them to come up with the final correlation coefficient, which can be used for classifying the targets. And again, we sketched the Wolf power spectrum density of 2 of targets, the target with 6 and 9.5 hertz, and with target with 6.5 and 8 hertz. And you can see that both the target and frequency are evoked properly in both of them. And these dual frequency aggregated SSMVPs, as you can see, outperforms regular SSMVP in terms of the accuracy and ITR if plot them across different time windows. And if you look at this table and the last column, again, we can notice that the bifold canonical correlation analysis fusion outperforms other counterparts, and which means that this is compatible to our own design. And the best result across each paradigm is bolded in this table. So in the next chapter, so all of the methods we have used so far were unsupervised, but in this section, we want to introduce supervised classifier for target identification tasks. We deploy deep learning-based design consisting of 5 fully connected dense layers. And as the color of the pixel of a video changes during the time, a potential will be evoked in the EG signal. And our goal is to find the superposed VPs caused by all the pixels of the video. And eccentricity, which is the distance of the pixel from the focal point, has high impact on the intensity of evoked signal. The further a movement is from the center of attention, the less it has impact on VP. And as it is shown in the picture, we group the pixels in this ring here. We group the pixels of each RGB layer based on their eccentricity. In other words, those pixels which have the same distance from the focal point are located in the same group. And the signals corresponding to pixels in each group are averaged to generate a tensor Z, which is here. And then we've fed this tensor is fed into the fully connected neural nets. Finally, apart from the VFE layer or the video feature extraction layer, we have 2 types of nonlinear projection. One for the representation of the video, and another one is for the EG signals. And these learnable projection embed both types of signals to the new space in such a way that the linear operations are applicable to the new space. And then now it's time to perform our previous linear canonical correlation analysis to get the good result. So I want to move on to the next slide. We don't have time for this part, but okay. If we perform our experiment, so we designed 4 SSMVP paradigms with 4 motion modes, and 5 men and 5 women between age 20 to 27 participate in this one. You can see the videos of these paradigms, and the left one is the resizing, and the right one is the rotation. So we perform 8-fold cross-validation and use user-specific training for each subject. And also, if you look at these columns, we see that our model outperforms its CNN counterparts in terms of accuracy and information transfer rate. And this is because the model avoids overfitting, and also it doesn't need a large training data set. And moreover, it provides more interpretation rather than the CNN for understanding the mechanism of classifier, because there's intuition behind the nonlinear projection. So as a summary of our contribution, as you mentioned, although the SSMVPs cause less fatigue and are more practical than SSVPs in Bcis systems, they're not as accurate as SSVPs. And our goal was to come up with the new types of SSMVP, which are accurate and practical. Basically, VP-based system has three main components, including stimulus paradigms, modulation algorithm, spatial filtering, and signal classification methods. And we enhance each of these components without changing others to make SSMVP robust enough. So we proposed novel SSMVP paradigm and assess their feasibility using a closed loop system. And also we proposed supervised and unsupervised classifiers to enhance the frequency recognition task. So as future work, we also design the single target motion visually with potentials. Here we have one single motion, and the targets are located around these motions. And we call this paradigm the nominal motion. And N2000 components are the main features of these types of MVPs. And a supervised technique can be used for classifying the target in these motions. And we segmented our time EEG signals into 300 milliseconds data epochs. And based on the correlation between the incoming data and the template signal, we can label an unknown EEG signal. Our future direction comes from another design. And in this work, we use the logo of the companies. And however, here we use the same frequency across all the targets. And we want to understand how we can distinguish between the EEG signals collected from the subject when they're looking at these paradigms. And last of all, we alter the videos of paradigms using, this is another direction, because if you look at the closed loop system that we have, we can replace the designer by the generative adversarial networks. And we can use the feedbacks for running a reinforcement learning algorithm based on the real-time feedback from EEG signals. Thank you for your attention.
Okay, thank you very much for this